Hello everyone, my name is Guilherme Bertola. I'm a chemical engineer. I'm a researcher on additive manufacturing, also known as 3D printing. I'm also a hobbyist in 3D printing, and it's a very nice project for me and a pastime, 3D printing. I am making a series of videos on 3D printing. It's more about teaching the field, and this video is focusing on 3D printing, slicing and making. So this is a video more focused on the slicers and more the general idea behind the parameters that we have. It's not a video focused on a specific slicer, and it's not a video on the general of 3D printing. So let's start by talking about slicing. In the process of 3D printing, we take a 3D model and we create a 3D computerized model and we create a 3D physical part. In order to do that, we need to tell our printer how to make it. And our printer, most 3D printers typically work in a layer by layer manner. We're going to be focusing on FFF printers or fused filament fabrication printers, which are just called filament printers. Those filament printers will do in a layer by layer filament or polymer deposition on those layers, and in this slice by slice manner recreate this 3D model into a 3D object. And the process of taking this 3D model and creating the steps on how to make our sample is called slicing, because we do have to slice this model into any numbers of layers to be able to create them. And during this slicing process is where we implement some machine parameters that are used to control some quality process of fabrication, like print speed or generation of support structures, and even temperature controls for different materials that we might want to print with. This slicing process creates a file called G-code. It's somewhat similar to your word processor softwares when you have something like a script, a play, an essay that you write into Microsoft Word, Pages, or Google Docs, and you save it into a file that's better to be printed to create a physical material to it, usually a printable document file or a PDF, right? And it's somewhat similar into that. We take this 3D model file, usually at .stl, .3mf, or .obj file, and we take those files, slice it, and create into steps and instructions on how to create this, which is the G code. G codes are read by the machine. They are machine readable instructions that usually typically starts with codes M, which are for machine instructions like heat up to this temperature, or things like assume that your position now is 0, or home your position. And other codes are there are G codes, like G0 or G1 are movement codes, are codes that move our head, our print head, to different locations on a Cartesian like 3D space, X, Y, Z. So if you open a G code, for example, that will create a rubber ducky, you see that you have thousands and thousands and thousands of lines of XYZ coordinates where you're actually, if you're following it, you're actually drawing your rubber ducky in a layer by layer manner. Can you write G code by hand? Yes. Should you write G code by hand? Absolutely not. Uh, it's, as I said, thousands and thousands of layers. That's why we have slicing softwares to do this job for us. So again, just as a short version of this slide, slicing is the process of taking the 3D model into a file called G-code that can then be put on the printer to generate our printed part. There are many slicing softwares available right now. If you have, for example, a Bambu Lab printer, you're probably going to use Bambu Studio. They're very well integrated with their own printers. For a more generalized approach, you have Prusa Slicer. Or if you're an old schooler in 3D printing like me, you can use Ultimaker Cura. I want to say those three are the three big ones that we see right now in 2026 for slicing. Back in my day when I first started this field was very much for hobbyists and people that were making their own printers with the rep movement. We had things like Slicer with a tree. We had Automatic Cura back then, although it was very different as Slicer. I'm very glad, things evolved and make things much easier for the common folk. And we had things like Simplify 3D is still around, but we want to say like those three slicers right now that I mentioned is the one that are most common right now. I mentioned that this video is not going to be focusing on any slicer in particular, but the images and some of the wordings you might see are Ultimaker Cura words and images. They are what I am going to be focusing more on. And on the video that I'm going to actually go through the step-by-step of slicing something and 3D printing something, I'm going to be using an Ultimaker Cura slicer. Well, let's go now talk about the structure of an FFF printed part or a 3D printed, fused filament fabrication part. This 3D printed part, it can be typically divided into some subparts. You have your model, but when you print it, it's actually consistent of its shell and what's inside of it. So your surface, your shell, and your infill. Not necessarily you're gonna have a solid part. Most likely you wanna have a part that's somewhat hollow. Also, not necessarily want a part that's completely hollow. Typically, when we print, we do something in between, something like a 15% hollow part with this internal structure that we call an infill. So your part can be divided at this outer part and this inner part, the shell and the infill. And or the walls and the infill. That's typically the wording used by Cura. But there are also parts that you're going to be printing and structures going to be printing that are not part of your actual model. For example, we're going to be using a rubber ducky as an example in this video, and there are things that are not going to be printed that are going to be printed that are not part of the rubber ducky. Some of those things are support structures. For example, you can see the beak of the rubber ducky. It's very hard to print something on air. On a filament printer, we actually have this molten plastic coming out of the extrusion nozzle. And if you just extrude something on air with nothing to support, it's gonna sag, it's gonna fall down. So if you have something to print on top of, for example, a support structure that's being printed with the rubber ducky, then you have something to print on top of, and you're gonna have a higher quality of your sample and actually have your sample being printed. Sometimes you cannot print it without support structures. So, but they are not part of your sample. You're gonna have to break them away. You're gonna remove them, and those are, as I mentioned, if applicable, are also printed alongside our structure. Another one is bed adhesion structures. Sometimes in a brand new printer, in a very well calibrated printer, you can just print your part without having to do anything extra. But sometimes, or for just being on the safer side, we print things like this blue region here. This part is the support structure, but this part here, you can see it's a little skirt that's just increasing the surface area, increasing the touching area that's touching the build plate or the print bed. I think it's called the build plate in print bed in Cura. But in the print bed, it's going to increase this area. You're going to have more things touching that bed, so you're going to have a better adhesion, and you have less chance of your printing coming loose during the printing process, or just not sticking to the bed and not being able to print, which was a big problem in older printers, which are much better right now. We have better surfaces. We don't have to use some of the older tricks that we had on our sleeves to make increasing bed adhesion. Well, we can now go look at the parameters we have available. And this is a little video about the current parameters we have. And like I said, we have a myriad of videos, parameters that we can change from and fine tune. But there are really just, I want to say, 6 types of parameters that we're going to be changing semi-regularly. When you take your printer out of the box nowadays, a brand new printer, you'll be able to just select one of the custom profiles in your slicer software that will be focused on your printer, and it will typically be plug and play. You're just gonna hit slice, not change anything, and you're gonna have your part out. But you definitely want to, if you're seeing this video, you definitely want to learn a little bit more about what are some of the parameters that you can change. And those are layer height, also known as print resolution, the wall top and bottom counts, the infill density and the infill types, the printhead and bed temperatures, the build plate adhesion structures, and the support structures. In this video here, I'm just showing you how many more parameters you can change. You can change print acceleration. You can change print jerk. I don't know if you can change print pop, but you can go up to like the third derivative of distance to control. There's plenty of things, different orderings and structures and properties and velocities and accelerations, and you can all fine tune this to really nail your part the way you want it to do. So finding and fine tuning those parameters is some of an art, but luckily for us nowadays we don't have to really fine tune them to get something. When you get the paper printer, you don't have to fine tune the jetability of your ink or the speed of the printer to really get nice quality printed parts or printed paper. The same thing for 3D printers. Nowadays, you have these custom profiles that you can just load. You can see on this image, we have a fast profile that's loading. You can just choose one of those profiles and hit slice, and you're gonna probably get a good quality part. But we're gonna look at how some of these affect and what those different parameters are. So the first one, and I want to say it's definitely the most important one, is layer height. Layer height will heavily affect not only the quality of your parts in a matter of it looks nicer or but also it's gonna affect things like the speed, how fast do you actually print your part. If you the layer height is how thin are those individual slices that we make. So the layer height is, for example, a 0.3 millimeters is gonna make that every 0.3 millimeters you cut your piece, and you're gonna have this 0.3 millimeter thick slices of sample of layer to create your 3D printed part. So you end up having this rougher edges, and you can actually see those layers lines easier. If you're printing something like a cube, you cannot really, it doesn't really make much difference. But if you have like smoother curves, you could think of like a topological study, a survey that people do in land, like civil engineers or architects might be familiar with. Uh, and those slices definitely do look like those topological curves that we see. So having these thick slices, as 0.3 millimeters is typically considered thick, you can actually have your print done pretty quickly and with this rough look to it. However, what most softwares consider the normal is a 0.2 millimeter or 200 micron layer height, which really just like makes it a little bit smoother, but doesn't take too much long to print. Typically, you'll think that a 0.1 millimeter would then be considered a smoother printer, and it does. It is a much smoother, much harder to see those like individual layers and those individual steps, but it does take a much longer time to print. If just by if you think that a singular layer takes a X amount of time, if you're printing on point 3, it's gonna be 3 times faster than printing on a point 1. It's not exactly that. There are other things that play, but you can have this generalized idea of, okay, printing on a point 1, it's gonna be 3 times. I will say don't go 3 times, but it's gonna be 3 times slower. There is this rule of thumb when I used to work in a makerspace that we used to follow, where your layer height, there's a range where you can actually make it. Uh, it's typically set by this empirical rule that we had, where we had 25% of the nozzle diameter being your lower bound and 75% of your nozzle diameter being the upper bound. So your nozzle diameter is the size of the hole of your nozzle. Typically, most printers come with a 0.4 nozzle. In a 0.4 nozzle, we have 25% of 0.4 is going to be 0.1, and 75% of 0.4 is going to be 0.3. And your sweet spot is going to be on that 50%. So typically, you're going to be using a 0.4 nozzle. So you can follow this 0.1 for being on the lower end, 0.3 being higher end, and 0.2 being that right in the middle. The explanation for those 25% and 75% are more empirical than having an explanation itself, but you can think of as, I don't say that I have not an explanation. I can spend a lot of time talking about rheology, polymer rheology here, and explaining why this is true. But what I want to say is that you can think of having, if you have something larger than 100% of your nozzle diameter, you just, there's no material that's gonna come out more than the diameter itself. Although again, I know die swelling from polymer processing, it doesn't matter. You can think of not having like larger than 100% of your nozzle diameter for layer. Your nozzle is not gonna be able to to remove more material than that. You're just not gonna have good adhesion. And what you want is actually have some sort of adhesion and compaction to make sure that the layers itself, the different layers are sticking together. If there's too large, we actually have something called delamination or delayering, where the layer doesn't stick together very well with the others because you're only, instead of having this very nice pushed together layers, you're gonna have layers that are barely touching, and they're gonna have a very, very weak part where you can just snap it off. So you really want to push a little bit lower than your nozzle diameter, and that's where 0.75 come in as your upper bound. And the lower bound for 0.25, you can think like if you have a very thin layer, you're pressing too much. You're gonna put too much pressure on the nozzle. You want to have like a lot of material coming out. This works if you have a very high quality material with like a lot of plasticizers, not your typical PLA. You want to use a PLA plus if you want to do like a very fine layer printing, because this is where clogging can happens, or like grinding or pressure problems. So if we follow that 25% rule and 75% rule, you're probably gonna have like a good time. And that's also why people sometimes refer to higher nozzle diameters as fast nozzles or faster printer, or like sometimes draft type print nozzles, like a zero point 0.6 or a zero point 0.8. If we follow the 75% rule, a zero point 0.8 will have a 0.6 millimeter. So it's going to be 6 times faster than a 0.1. So you see how those like higher, we can go higher if we have higher nozzles, but we sacrifice resolution and quality. But if you really want to make something fast, you can definitely use that. Although nowadays printer printers itself are much faster than um, other printers. Okay, So the second part that will be of somewhat big importance is the wall top and bottom counts. Those are all different parameters. The wall, the top and bottom, sometimes they're related. Sometimes they're one parameter, top and bottom, or sometimes they're different, split into top and bottom counts. Uh, you can either configure them to be, for example, in by a number of walls. You can see here a two-walled uh, slice of the rubber ducky and a three-walled slice of the rubber ducky. Uh, Typically, Kuria, if it trusts itself, will use two walls, but on the safer side, sometimes it will suggest three walls. You can go for five walls on top and bottom to make sure that you're gonna have a nice last wall, or we can call like the shell or the skin of our part. You can see that Kura does color it in two different colors, green being the internal walls and red being the external walls. The internal walls, you really don't care if they look ugly because you're not going to be able to see them. So sometimes you can control things like print speed for those different walls. You can have a faster printing speed where you end up making, an uglier looking part, but if you do this on the inside walls, you don't really see them. Then you can do a very slow and more calm and higher quality skin or outer wall. If you're having parts that you're seeing holes through it, or you're feeling that they're a little bit weaker, you can intensify their strength uh, and also take a little bit longer to print, but making it look typically nicer and also stronger by increasing the wall counts. Again, typical for walls for the skin of the part, it's three walls, and for top and bottoms, we usually do five. You can also do three. Three is fine, but five, you're just gonna have a little bit more less chance of having any holes or deformations on that that part. After that, we talk about the inner parts of our model, the infill. And the infill, as I mentioned before, it can have different densities. You can have a completely hollow part, which will be a 0% infill, or a 100% infill, which will be a completely solid part. Uh, Typically, we have values from 15% all the way to 30% infill. If you're going above 30%, you're not gonna have like a much stronger part. You have diminishing returns above 30%. And you're not gonna save a lot of time than just printing a solid part. So that's why we typically have 30%. And lower the 15%, depending on the infill type, we're gonna have to increase number of walls or number of top and bottom layers. So to actually have a nice looking part or if a good structure. So that's why typically we have this lower bound of 15%. So here's just an example of what a 15% density of infill and a 30% density of infill looks like. Those two infill types are called grid infill, and there's many different patterns and types that we can use. Grid infill, I'm gonna say it's typically what it's generally just used. It's just lines on a grid. It does a great job, creates the structure, is strong enough for most applications, and it's very fast to print. But we used to have like honeycomb infills. We don't use that anymore as much because they take somewhat long to print. And if you really want that strength that came with the honeycomb, there are trihex infills right now that combines the hexagon and triangles to create this very strong infill while also being composed of just straight lines, which makes it much faster to print. We have triangular infills, again, very, very good, very strong. We have 3D infills like this cubic one. It does look like a trihex if you look at it, but it's actually just like tilted cubes. So not only it has this forces to the side, but it's also, it can take forces from any direction. And one very famous infill that can handle any forces from any direction is the gyroid infill, as we can see here. And the other parameter that we can see and configure is the print bed temperature. And this is a very important parameter to configure, but at the same time, it's a very set and forget value because it's typically provided by the filament manufacturer or the type of filament that you're going to be using. Filament manufacturers are going to put ranges, but your slicer will select one value for you. There are some suggested parameters there for PLA, ABS, PETG, and TPU. If you have like a 3D printer and you're gonna see, for example, a different value on ABS, for example, seeing the bed temperature being 100, it's not wrong because each printer will have some different needs, or each filament that you use will have those different needs. But typically, if you buy a filament, you find the temperature that works for it. Typically, you find the temperature that works for that type of material, PLA, for example, and then you buy any brand, it's typically going to work very nice. But you can do the small adjustments that increase the flowability, lower the viscosity of your samples when you increase the temperature, for example. So it's gonna make like flowability and spreading a little bit easier. Or if it's spreading too much, you wanna might dial back on the temperature. So they're all things that you can control. That are very important to make sure that you're not putting the wrong temperature on the printer or for the filaments. You do not want to burn your PLA. The reason why we use those temperatures is that those are the temperatures where some of the amorphous polymers really are in this more flowable states. The more crystalline polymers, they are in this melt state, so melting temperature. For the print bed temperature, we usually try to reach the glass transition temperature, which is where it becomes softer and they stop structuring of these crystals. But instead of you going and learning material science and polymer science and figuring this out, you can just read the box that your filament came with, and it's gonna probably tell you which temperature for the print bed and which temperature for the print head. And we're very happy that modern slicers have this. We just select the material and they're gonna have a fine-tuned temperature for us for the material we're gonna be using. PLA, ABS, PETG, TPU, PP, nylon, and all those different types of filaments, HIPS, ASA, whatever. Uh, Another thing that we can take a look are those extra structures that we're going to print that are not part of our printer itself, which is we're going to be starting with the build plate adhesion. Here I have some images of a raft, a skirt and a brim, or a brim and a skirt. Cura calls this a brim and calls this a skirt and this a brim. I I didn't learn it that way. I run them different ways, but they're very similar among themselves. Uh, as I mentioned before, there are these extra printed parts, extra printed sections of your part that will increase the chances of your printing working. Will make sure that it's very well adhered, very well stuck to your build plate, to your print bed. Uh, Back in the day, we would use tricks like painter's tapes and glue sticks and using hairspray, things like that to make our surfaces easier to stick to. nowadays we have removable plates with customized structures that can create this very nice adhesion with our parts. Most slicers offer at least those three build plate adhesion types. This brims that is gonna outline this printed part that's not only is gonna help you know where the printed part is going to be, but also purges some material so you make sure that when you start printing, you actually have material on your print head. So this purging that the brim does, it's very important. So you make sure that when you're actually printing, you're ready to go with material in your print head. Skirts are very similar to the brims, but they touch the part. So not only they purge, they act as purging zones, but they also increase that surface area. And by the increasing of that surface area, we have a better adhesion. And refs, they're more complex. You typically print this very thick, very over extruded parts and layers onto our build plate and print on top of that, because the idea is that the better adhesion is going to be to the material itself. So the PLA is going to adhere better to PLA itself. So that's why we create this very thick, very over extruded lines and layers to have this our parts printed on top of this. And lastly, but not least, we have the support structures. As I mentioned, complex overhangs when you have in 3D printing can't really be printed without supports. I mean, you can sometimes print overhangs, but typically you have overhangs with an angle greater than 45 degrees. For example, you have 45 degrees here. If you have an angle greater than that, you have like more material, more chance to sag. If it's less than that, you actually can build on top of just like hanging on to that parts over there. So lower than 45 degrees typically it's okay, but higher than 45 degrees you start gonna have sagging and failure of reprints. So that's why we introduced those supports. Support can be made out of the same material as the part itself. For example, if you have just a single filament printer, you can have supports. You make supports of a very thin lines that are typically very easy to break away and to remove. But you can also use, if you have a multi-material printer, you can also use different filaments, for example, PVA or HIPs, which are dissolvable materials, where instead of having to break away your parts, you can just dunk it into a solution. For example, PVA, it's water, and over time it's gonna dissolve, and you're only gonna have your printed part. The support placement is also a very important thing to configure. Typically, you can select for it to only create supports where you're gonna directly touch the build plate, meaning you're not gonna have a part-to-part support. And you can look at the rubber ducky for this. You can see that some of the support is actually hanging itself on the rubber duck itself. So this might have like a uglier outlook, a worser skin, might requiring some post-processing to your part. Uh, but you also have more supports and you have a higher chance of having like a nicer beak done, or the proper beak being printed, instead of just using things that are able to touch the build plate like this initial part here. One alternative to trying to avoid this is changing your type of support. Typically, you have two types of support. You have line supports. They're gonna cover this more area and they're gonna create very thin lines, like in a zigzag manner or in a concentric manner, or different shapes than they can do, typically on a zigzag. Uh, and those are very easy to break, but they need to be directly underneath the part that needs overhang. If you have a tree-like support, you actually create these branches, which are typically easier to remove, as you can just remove a branch and the other branches usually come off with. but you actually have less touching portions, so you might have a worse underneath support look to your parts. But since it can do this 45-degree angles movements, you can actually have something like this where the support starts outside of the part and goes into an area that's typically inside of the part and then does the support. Meaning, instead of having to break this from both here and here, you can just break it from here, and it's gonna be easier to remove those ports. Whether a line support or a tree support is the right support for your part, it's gonna depend on your part. But that's it. That's a general view of those parameters we have in slicing. Thank you very much for watching. I'm going to be working on the other videos, and I really appreciate your time. Thank you very much.